The year was 1955. World War II was 10 years behind us. The baby boom was on. Flight on jet airplanes had become a common occurrence. And in a cornfield west of Los Angeles, a new industry took root.
Effective Monday, November 7th, 1955, the Propulsion Center activities will become the Rocketdyne division of North American Aviation.
Men and women from all walks of life came together to apply their skill and talent to the building of liquid rocket engines. They were to become partners in some of the most significant events of the 20th century. For Rocketdyne was destined to lead the way as man entered the age of space exploration. The group that formed the nucleus of Rocketdyne back in 1955 had its beginnings 10 years earlier. North American Aviation formed the Technical Research Laboratory to study the feasibility of developing guided missiles for the United States. Study of German World War II rocket propulsion systems, primarily the notorious V-2, soon led to a contract to develop the Navajo ground-to-ground missile for the Air Force. The historic first subscale engine firing in the company's parking lot was followed by an intensive development program.
Our temporary test station is small in area, and consequently we have some interferences in making our tests. In spite of this handicap, our operating crews have been able to make as many as 12 one-minute rocket motor runs in a single day.
The need for a major rocket engine test site was apparent. In 1947, a secluded range in the Santa Susana Mountains was selected. Later known as Rocketdyne Santa Susana Field Laboratory, it became the nation's first high-thrust rocket engine test facility. In 1947, employment had grown to over 500 persons, and the group now named Aerophysics Laboratory was established as a separate department of North American. Development effort intensified, and propulsion personnel were designated as part of the Missile and Control Equipment, or MACE, organization. In March 1950, the roar of the Navajo marked the first full-thrust test of a major American rocket engine. It signaled the birth of American rocket power. Out of the pioneering Navajo program came not only its own engines, but also the technology for those of the Redstone, Jupiter, Thor, and Atlas ballistic missiles. By the end of 1950, the MACE propulsion group had grown to over 1,600 people, and major events came with increasing frequency. A rocket engine for the Cook sled began its record of over 100 runs without failure. The Redstone engine program was started for the Army. Small aircraft rockets were developed to support Korean War needs. The tubular wall thrust chamber replaced the double wall, a key technology breakthrough, and the rocket engine advancement program began to probe beyond the state-of-the-art established by the Navajo. The contributions of this effort were major, improving the Navajo and providing key design concepts for the future Atlas. Mid-1953 saw the first launch of the Redstone, the first American high-thrust ballistic missile. In early 1954, the first contract leading to the Atlas ICBM engine system was awarded to MACE and was soon followed by the first Atlas booster firing in 1955. Two more engine contracts were received, the Air Force Thor and Army Jupiter, both intermediate-range ballistic missiles. Effort on all programs was intense. The government had given them the highest national priority to meet the new world threat caused by the first Soviet hydrogen bomb test in 1953 and evidence of their strong ballistic missile program. With this sense of urgency, it was obvious that rocket engine development would continue to accelerate. And so, in November 1955, divisional status for the fast-growing group was established. Rocketdyne was born, and its first mission was clear. The general manager and later president of the division was Sam Hoffman, who had joined the group in 1949. He was to lead the organization through 1970, always emphasizing the importance of the individual.
I believe that there is in each of us an inherent desire to do good work. That you will agree with me that such cliches as "to err is human" and "you can't win them all" are simply excuses for mediocrity in today's technology. It is you and I, the people who do the jobs, not the machines invented to help us, upon whom success or failure depends.
Sam Hoffman's challenge was quickly answered. With 5 major engine programs in progress, Rocketdyne set to work. By the end of 1955, over 2,500 personnel relocated to Canoga Park from the Slauson, Beverly Hills, and Deering facilities. Another 500 were added in 1956, the year noted for the first deliveries of Atlas, Thor, and Jupiter engines. Development of smaller engines expanded as well. A Navy contract led to the Super Performance Rocket Augmentation System for fighter aircraft, the AR engine. As engines qualified for production status, the demand for manufacturing space outgrew the local facilities. The Air Force provided a plant in Neosho, Missouri, where Rocketdyne assembled and tested thousands of engines, both large and small, over the next 12 years. 1957 saw the first flight test of the Atlas. And that same year, the Thor. A remarkable achievement in only 3 years development time.
The Atlas Thor program is even more remarkable in that it has endured throughout the entire life of the Rocketdyne division. During that time, Atlas and Thor Delta has launched more than 1,000 vehicles. How could any one of us predict that some of the original employees would still be working on the program 30 years later? The continuation of these cost-effective and reliable programs is a tribute to everyone in the Rocketdyne division, including their sons and daughters, who are now employed as members of the Atlas Delta team.
But the successes of the Atlas and Thor spelled the end of the pioneer Navajo. In mid-1957, the program, which had contributed so much, was canceled. Technology had passed it by. The abrupt shutdown of such a major program impacted workloads dramatically. Yet this event was soon overshadowed by the electrifying news that the Soviet Union had orbited the world's first artificial satellite. Sputnik 1 brought the dawn of a new era. 4 months later, in January 1958, using a Redstone-powered Jupiter C vehicle, the United States orbited the Explorer 1. America's pride rebounded. With the maturing of the national defense missile programs, the country's attention turned to space. But the conquest of space called for massive power, many times that of existing vehicles. Thus, the first big booster engine system for the Apollo program had its beginnings through the Army's Advanced Research Project Agency. 8 uprated Jupiter engines, later known as H-1s, were clustered to power the Saturn I first stage. And development was started on the mightiest of them all, the F-1. 5 of these 1,500,000-pound thrust engines were slated to power the first stage of the Saturn V moon vehicle. While big booster power was being developed, the Redstone, already proven in more than 50 missions, was awarded the near-term task of launching the first flights in NASA's Project Mercury program. And on May 1st, 1961, Alan Shepard became America's first man in space. In a 15-minute suborbital flight, he took the first step in America's journey to the moon. As Rocketdyne entered the 60s, its involvement in rocketry had broadened to include solid rocket production. Astrodyne, a McGregor, Texas company, was acquired. During the next 20 years before it was resold, the solid rocket division produced thousands of rocket motors in support of Department of Defense needs. But the mainstream effort continued to be the advancement of liquid rocketry. The upper stage Saturn V engine, the oxygen-hydrogen J-2, moved into development as the Redstone and Jupiter engines were phased out. Rocketdyne employment climbed to 10,000 with 2,250 at Santa Susana. In 1961, at the rocket test site at Edwards Air Force Base, an F-1 test reached the unprecedented thrust level of 1,640,000 pounds. And later the same year, the Saturn I space vehicle made the first of 14 flawless flights, paving the way for the Saturn V. Rocketdyne's reputation continued to build with the Atlas Mercury orbital journey of John Glenn. And Rocketdyne-powered satellite launches for weather, communications, and Earth surveillance became commonplace. The Mariner spacecraft traveled past Venus into the vast reaches of unexplored space, another major United States first. The Gemini spacecraft program called on Rocketdyne for the orbital attitude and re-entry control systems. Small engine activity continued to expand with development of the attitude control system for Titan III, the Apollo Command Module reaction control engines, and Agena secondary propulsion. The P-4 was built to power a target drone, and a propulsion system was developed for the Army's Lance battlefield missile. In 1965 and 66, the world watched as Gemini astronauts walked in space and perfected their skills in precision, rendezvous, and docking maneuvers. The goal of landing man on the moon drew ever closer. Major technological breakthroughs on the F-1 and J-2 engines for the Saturn V moon vehicle rapidly advanced the programs through development and test into production. By 1965, Santa Susana had amassed a total of more than 200,000 tests. And in 1967, the year North American merged with Rockwell, overall Rocketdyne employment had reached 16,000 as new headquarters and production facilities were added.
F-1 and J-2 assembly moved into Building 3 as the Rocketdyne team prepared to meet the Apollo challenge of a man on the moon before the 70s. The concept of assembling F-1 engines in a vertical attitude was developed and is still in use today. This method of assembly improved quality and productivity, thus allowing the Rocketdyne team to meet schedule with a quality product at minimum cost.
As the Apollo program moved forward, the number of satellite launches continued to mount. The Rocketdyne-powered Thor rocket, the nation's most frequently used space booster, marked its 200th launch. Over 100 Atlas Agena missions were completed. The Atlas launched the Mariner for the first Mars flyby, and the Ranger series for close-up mapping of moon terrain. Man himself was soon to follow as the Saturn V moon vehicle came of age. After 2 unmanned flights, the Mammoth rocket, towering over 16 stories high, powered the first of 4 final steps to the moon by placing 3 astronauts in lunar orbit. 3 more manned flights completed system checkout and perfected mission procedures. And then, man's dream was realized. On 20 July 1969, astronaut Neil Armstrong set foot on the moon.
It's one small step for man, one giant leap for mankind.
For Rocketdyne, it was an especially proud moment, a time to remember. The 30 Rocketdyne engines on Saturn Apollo continued their perfect performance during the remaining 6 Apollo moon missions. Then, with all program objectives achieved, the boldest chapter in space history came to a close. While the Apollo program captured headlines, research had continued on the next generation of rocket engines. The unique aerospike nozzle was evaluated and was an early candidate for use on the new Space Shuttle Orbiter project. But the greatest promise lay in a conventional chamber-topping cycle engine operating on hydrogen and oxygen. The most intensive proposal effort in Rocketdyne history was rewarded by program capture in 1971. The effort was guided by Sam Hoffman's successor, Bill Brennan. An unequaled record, plus outstanding design and test achievements during the proposal phase, won Rocketdyne the greatest challenge ever in rocket development. The Space Shuttle main engine program became the central effort for the foreseeable future. But until early development work could be completed, staffing needs were low. Steadily declining employment bottomed at 3,000 in 1972 before growth resumed. In 1973, a dramatic series of Skylab launches provided temporary space stations for extended research periods. An uprated Thor was developed to boost the Delta vehicle. Over the coming years, satellite launches reached into the hundreds, and by 1980, total Atlas, Thor, and Delta flights since 1954 had reached 961. The launch of the last Saturn 1B in 1975 marked Rocketdyne's role in the Apollo-Soyuz test project. By 1976, when Norm Riker became the new division president, employment had rebounded to 4,000, and facility refurbishing gave the division a new look. The same year, the first full-thrust main stage test of an SSME was conducted successfully at the National Space Technology Laboratory in Mississippi. And Santa Susana's Coca test area reached full activation. Another major proposal was submitted in 1977 as the company bid on the Peacekeeper program. Capture of the award led to Rocketdyne's establishment as a builder of complete stage systems. Starting earlier in the 70s, emphasis had been placed on diversification by applying the division's wealth of rocket technology to new fields. Spin-off projects have included power jet, torpedo ejection, solar receiver, thermal storage, advanced heat exchanger, downhole steam generator, and in the most significant technology transfer of all, Rocketdyne applied its expertise to high-energy laser development. Many basic rocket theories and disciplines proved common to the burgeoning field of laser science as projects grew from small laboratory experiments to major test installations. Today, Rocketdyne is recognized as a leader in the research and manufacture of laser and laser-related hardware. The flight of the first shuttle orbiter drew nearer as the 80s approached. In 1979, the first flight engine was delivered to NASA. In early 1980, SSME testing time passed the 65,000-second mark, and soon afterward, the 3 engines of Columbia proved their flight readiness. Then, on 12 April 1981, the first flight of Columbia ushered in the age of space transportation. Now, after 4 years of launches, the Space Shuttle main engine's record has firmly established it as the United States' primary space booster for the foreseeable future. While the SSME was being developed, Rocketdyne mounted a parallel program to define the needs for orbital transfer propulsion, anticipating man's expanding role in space. Now there exists a broad inventory of engines designed to meet a variety of requirements for moving satellites and other vehicles into higher orbit. During the same period, the Peacekeeper Stage 4 program advanced rapidly through design and development phases. The Rocketdyne produced axial engine and attitude control engines were tested individually and in system test beds at the Santa Susana Field Laboratory. The first launch of the Peacekeeper missile took place on 17 June 1983, signaling the start of a series of successful flights highlighted by flawless Stage 4 performance. '84 also brought a major organizational realignment. Atomics International and the Energy Technology Engineering Center of the Rockwell Energy Systems Group merged with Rocketdyne, uniting the corporation's power specialists. Like Rocketdyne, the Atomics International business area had its roots with the Aerophysics Laboratory in the late 1940s, becoming a separate division in 1955. Dedicated to the research and development of nuclear energy, the group built and operated 39 nuclear reactors and critical facilities in the coming years. Early projects led to the activation in 1957 of the first nuclear reactor to produce electrical power for a utility grid. The plant, located in Santa Susana, operated for over 36,000 hours. This sodium reactor experiment provided the expertise for the design, construction, and 1962 startup of the Hallam Nuclear Power Facility in Nebraska. And of major significance was AI's performance on the System for Nuclear Auxiliary Power, or SNAP, project. In 1965, the SNAP-10A system became the only nuclear reactor in space, operating as programmed for over 1,000 hours. The Energy Technology Engineering Center is a Department of Energy multi-program field laboratory located at Santa Susana. Chartered in 1966, ETech has concentrated on the science of applied engineering development for nuclear power plants, and more recently, they have become involved with extraterrestrial power systems for future space applications. In 1975, Atomics International captured the contract to manage, operate, and maintain the U.S. government's nuclear facility located in the Rocky Flats plant at Golden, Colorado. A similar contract for the Department of Energy's Hanford, Washington operations was earned in 1977. Over the years, operation of numerous sodium test loops, including one rated at 100,000 gallons per minute, has made Atomics International a world leader in liquid metal reactor technology.
Our 30 years of support to the nation's space and energy programs could only be achieved through the commitment of each employee to the excellence of our hardware. It has taken outstanding designs by our engineers, pride in workmanship by skilled manufacturing craftsmen, attention to detail by quality, and the accurate on-time support of the total organization to achieve this leadership position. It has not always been easy. You have made significant personal sacrifices to achieve this record. Each of you should be proud of the role you have played in this 30 years of excellence.
Rocketdyne continues to advance the state-of-the-art in a number of high-technology areas, leading the way as the free world's foremost developer of space power systems. And it does so with the resolve, the dedication, and the quiet confidence that comes with a record of 30 years of excellence.